Okay, we're going to talk about subsets in this video. So in your textbook, this is in section 2.2. It's on subsets. Okay, before I do that, I want to mention the idea of Venn diagrams. This is a good place to bring it in. So a Venn diagram is a diagram that helps you illustrate the relationships between sets. They're very similar to Euler diagrams, like when you investigate syllogisms, which if you're in this particular class, at the time of making this video, we did that in the previous homework assignment. The idea with these Venn diagrams is you always start with a universal set, and let's just let this be all Hawkeye students. And I'm just going to try to make this easy as possible. So we could think all Hawkeye students enrolled spring of 2019 or whatever semester it is. Okay, and so this is the universal set. And what this is for this particular example, I'm just interested in the set of all Hawkeye students, and then I'll take different groups of Hawkeye students, and then I can illustrate the relationship between those students. So we'll let set F here. This will be full-time students, full-time Hawkeye students. Okay, and then let's let set W be Hawkeye students who work full-time. And we can just say that's 40 hours or more. Or 40 hours or more per week is full-time, let's say. Okay, so we have these two sets. The universal set is all Hawkeye students. Okay. And then I'm going to picture that with the square. So these are all Hawkeye students. And then I got these two sets, F and W. So they have some sort of relationship with one another. And let me just give you some possible examples. We could have, this is the set of all full-time students. This is the set of all students who work full-time. So this particular diagram says something about the relationship of those two sets. And in this case, what it's saying is that those two sets are separate. They don't have any students in common. You either work full-time, or you go to school full-time, or you work full-time, but there's nobody that does both. And oftentimes, when I'm actually teaching this in front of the class, I'll have a student raise their hand and say, well, I actually work full-time and go to school full-time. And so they would be an example that would actually show that this isn't the right relationship. Most likely, there's going to be some students that do both. So that's not the right relationship. So I could try another one. What if I did this? I said, this is the students that go to school full-time. This is the students that work full-time. Okay, well, this is saying something about the two sets. And in this case, it says here, all the students that work full-time, or that go to school full-time, also work full-time. And that's definitely not true. There's a lot of students that go to school full-time that don't work full-time. And usually a class that I'm teaching will have a lot of students that fit that category. Notice this is the all A's are B's relationship from Euler diagram. So like all students that go to school full-time work full-time, and you'd put the F circle inside the W circle. Okay? And that's certainly not the case. Okay? So what would the right relationship be? So if you want, you could pause the video here and draw what you think the right relationship might be. Okay, let's see if you got that correct here. So I would say that the right relationship is that these two sets overlap, and it would look kind of like this. These would be the students that all work full-time or go to school full-time. These would be the students that work full-time. You got some students that do both. You got a lot of students that go to school full-time but don't work full-time. And then you got a lot of students that work full-time but are just going to school part-time here. Okay? So that's probably a diagram of the relationship between those two sets. So you can see then how Venn diagrams might be helpful, and you can kind of diagram out what might be going on between the sets. Okay? So now let's talk about a really important relationship, and this is the subset relationship. Okay? Let me give you an example here. Let's let U be all Hawkeye students. M will be all the Hawkeye students enrolled in a math class. And then we'll let C be all the Hawkeye students enrolled in this class. So see if you could diagram what the relationship would be between these sets. If you want, go ahead, pause the video and see if you could diagram the relationship. Okay, so let's see if you got this correct. So you'd have like the set of all Hawkeye students here enrolled in a math class. Now notice if you're enrolled in this class, this is a math class. So you would have to be inside here, and that would be C. So C is kind of a smaller subset of this bigger set, M. And that is the relationship that we're going to be looking at here. It's called the subset relationship. Okay? We would say C is a subset of, let me move this over. C is a subset of M. Okay, and what we would write is I would write C, and then this is like a U on its side with a line underneath. And this is the symbol for subset. And then I could put M. So this is how I would write C is a subset of M. And the definition here, the technical definition, is the following. We would say C is a subset of M if all the elements in C are contained in M. So that is the actual definition. C would be a subset of M if all the elements in C are contained in M. And so certainly all of us in our class are enrolled in a math class because our class is a math class. Okay, so that C would be the subset of M there. So let's actually, using this definition, try a few examples. So are these true or false here? If I said something like A, C, 3 is a subset of A, B, C, 1, 2, 3. What do you think? The answer is yes, it is a subset, because A is contained there, C is contained there, and 3 is contained there. So that would be true. Okay? Well, what about this? A, C, E is a subset of A, B, C, 1, 2, 3. Would that be true? Well, it's actually, what do you think? Is it true? It's actually false, right? Because, and you can see A is contained over there and C is contained over there, but then when we check for an E, there is no E over there. And so that means it's not a subset. So we would write a line through it. ACE is not a subset of A, B, C, 1, 2, 3. And the way we know is we can find an element over here that's not over there. So let's try another one. Make it a little more tricky. 7, 1, 3 is a subset of 10, 1, 5, 3, 11, 6, 7. So So would this be a subset of that? Okay, I'll let you look at it, think. What do you think? And it actually is. How do we know? Well, here we got to be careful because the numbers are all jumbled up. We got to see, is there a 7? Yes. A 1? Yes. 3? Yes. They are all over here. So it is a subset. So what about the following one? What if I said A, B, C is a subset of A, B, C? What do you think? Well, at first you might think, well, no, it's not, because this isn't a smaller group contained inside a larger set. And I get that, because we think of subsets as being these smaller sets contained within a larger set. But remember, the actual definition here, the way we defined it, is C is a subset of M if all the elements in C are contained in M. And so if I check, A is over there, B is over there, and C is over there. So actually, by the definition, this ABC would be a subset of ABC. And we get the following fact here, that every set is a subset of itself. Every set is a subset of itself. Okay. What about this? The empty set is a subset of A, B, C. What do you think? So again, this is a little tricky here. This is actually true, okay, by the definition. So are all the elements here in the empty set contained over here? Actually, they are. You see, there are no elements over here, so there's no way that this can fail to not be a subset. For example, like the one up here, E was not over here. So to show this was not a subset, I found an element over here that wasn't over there. Well, I'm just not going to find any elements here, okay, that aren't over there. So technically, by definition, it is a subset. So you get another fact, and that fact is the empty set is a subset of every other set. Okay, the empty set is a subset of every other set. Okay, so now a few other concepts here. I want to introduce the idea of a proper subset here, and to do that, I'm going to list out all the elements in the set, or I'm sorry, I'm going to list out all the subsets of the set A, B, C. So you might want to try to do that. You could pause the video and try to list out all the possible subsets that you could make. And maybe if you want to do that here, let me show you a formula. There's a formula that says 2 to the n is equal to the number of possible subsets of a given set. And this is where n is the size of the set that you're wondering. So like this set here has 3 elements. So I would do 2 to the third, and that's 2 times 2 times 2, and that means I would get 8 possible subsets. So when you do this, you should have 8 possible subsets. So if you want to try, hit pause and see if you can find them all. Okay, let's see how you did here. Oh, you know what? Let me move that over here. Okay. Let's see how you did. So the set A here is one possibility. B is another subset. C is another subset. AB would be another subset. AC is a subset. BC is a subset. The set ABC would be a subset. Every set is a subset of itself. And, of course, the empty set is a subset. The subset is the empty set is a subset of every other set. So there you go, 1, 2, 3, 4, 5, 6, 7, 8. Those would be all the subsets. Okay? So now all of the subsets of this set would be proper subsets except for one set. So I'm going to circle all the proper subsets. Okay? So these are all the proper ones. What set is not a proper subset? And that would be the set itself. Okay? So all the ones that are actually smaller than the original set, those are all the proper subsets. Those are the proper subsets. Okay, so for example, I would have like AB is a proper subset of ABC. That would be true. The empty set is a proper subset of ABC. That is true. Okay, ABC is not a proper subset of ABC. You see, that's the one subset. That is a subset, but it's not a proper subset. That's the one subset that's not a proper subset. All these other subsets are proper subsets. So notice A, B, C is a subset of A, B, C. That would be true because every set is a subset of itself. But it's not a proper subset. Okay? So one way of thinking about this subset symbol is this is kind of like a less than symbol, a strictly less than, or a less than or equal to symbol, the line under it. This is like less than or equal to. Okay? And what you have here is that ABC is less than or equal to ABC, but ABC is not strictly less than ABC. But AB is strictly less than ABC. The empty set is strictly less than ABC. Okay, so that's kind of how that symbol is used. Now let me show you one other example using this formula up here. So notice when you do this, it's always going to be 2 raised to, and this is going to be the number of elements in the set. Make sure that you don't square the elements. Sometimes people will square it. So if I have a set A, B, C, 1, 2, 3, okay, and I want to know how many subsets there are. Okay, there's 6 elements there, so it'd be 2 to the 6. Okay, so this is not the same as 6 squared. It's not 36. It's 2 times 2 times 2 times 2, 6 times. And you could use a calculator to find it if you wanted to. In fact, I have one right up here. I can show you. You would do 2, and then you would use the exponent button right there, this arrow kind of pointing to where the exponent would be. And then I would have a 6, and I would get 64. So there would be 64 subsets. So that would be a lot of work to list out all those possible subsets. Okay. Now let me show you an application of this formula that's kind of neat. And then we'll end with that. So suppose there's a salad bar. Okay. And they got a nice green salad mix. And then they got some toppings here. Let's say the toppings are onions. I'll use O. We'll say peppers. Let's say eggs. We'll say bacon bits. And we'll say cheese. And, of course, croutons. That's like a C too. I'll say K for croutons or something. In other words, we have 1, 2, 3, 4, 5, 6 different toppings. My salad can have 6 different toppings. Notice, if I don't choose any of the toppings, it's like the empty set. This empty set would be just the green lettuce. Just lettuce. Okay? This would be someone doing bacon bits, cheese, and croutons. They would have just those three on there. Oh, and you could put some dressings. I didn't think of dressings. But do you see that all the possible salads they could make, okay, and one would be O, P, E, B, C, and K, and this would be a salad with all the toppings on it. Okay, so if you want to know how many possible salads there are, okay, how many possible salads, you would just do 2 to the 6. There's 64 salads that could be made with those toppings. You could have 64 different salads. So you would just have the list of the toppings. You'd count how many toppings. You would use this formula to get the number of salads. Okay? Let me show you one other thing, too. If I wanted to know the number of proper subsets for a given set, what I would do, like this set, how many proper subsets are there? 2 to the 6, and then you would just subtract 1. So it would be 64 minus 1, which is 63. Okay? And it's always going to be minus 1 because what you're doing is you're subtracting the set itself. Okay, so for example, there's 8 subsets to this. 8 subsets, but there's 7 proper subsets. There would be 64 subsets here. 64 subsets to this, but there's 63 proper subsets. Okay, so that's something else. Okay, bunch of examples here involving subsets, so hopefully this helps. I'll let you work on the homework assignments here. Hopefully this is a useful video.